Hello and welcome to helpyourmath.com. In this video, we're going to look at the graphs of cosecant and secant functions. Before we get started, here's my best advice. If you're asked to graph a cosecant function, look at the sine function with the same a, b, c, d values. The x values for the two graphs will be the same, and the y values will be reciprocals of each other. The same is true for sine and secant graphs. So look at the corresponding cosine graph, and look at the reciprocals of those y values. By now, we hopefully are more comfortable with sine and cosine graphs, and that's just going to be the best way to graph cosecant and secant. Since the parent functions of sine and cosine graphs have a range from -1 to 1, the reciprocal functions have ranges of the reciprocals of those. Oh, I forgot the 1 didn't appear. What? And it would be from -infinity to -1, and then from 1 to infinity. I don't know why the 1 didn't appear, but it should be there. So they look really fun and interesting, and the secant and cosecant graphs kind of look like parabolas, but there's a big space between where they are, and they're not parabolas, they're parabolas between asymptotes. Remember that a full period for a cosecant or secant graph actually requires 3 asymptotes, right? Because it's kind of like a downward looking parabola and then upward, and that's going to be a full cycle, right? We need to hit everything. So one full period actually includes like 2 little pieces of graphs. All right, let's get started. We're going to sketch a graph of, and we're going to start with cosine 2x, and then we'll look at secant of 2x next. For y equals cosine of 2x, let's label what we know. We know that a is 1, so the amplitude is 1. B is 2, so the period, remember how to calculate the period for a cosine or sine graph? You do 2 pi divided by b, so 2 pi over 2. We're going to have a period of pi. Next, what we want to look at are the increments that we're going to use to find some key points here. And the increments, we take the period and we divide it by 4. So we're looking at pi over 4s as our period, as our increments. And now we might set up some key points. We have x and y, and we're starting at 0. And then the increments we're going to be adding on pi over 4, so we'll have pi over 4. 2 pi over 4 will be pi over 2. 3 pi over 4 and pi. This should match the period since there's no c value, and it does. Yay! Okay, what about our y values? So our y values, they start, this is cosine, so cosine starts at the maximum, goes down to the minimum, and back up to the maximum. Since the amplitude is 1, it's going to start at 1, go down to 0, down to -1, back to 0, back up to 1. Okay, so let's look at that. We'll go by pi over 4 units. So there's pi over 4, here's pi over 2, 3 pi over 4, pi. That's going to be one period. Now the next period we'll have 5 pi over 4, 6 pi over 4, 7 pi over 4, 2 pi. Go ahead and draw those. And we know the midline is going to be at 0. And we can just graph these points. So we have 0, 1, pi over 4, 0, down to the bottom at -1, back to 0, back up to the top at 1. We can do our second period if we want to. Back down to 0, down to -1, back up to 0, up to +1 at 2 pi. Okay, so now, how does this help us? Oh, let's make a nice smooth curve here. So we're going to do go down, up, down. All right, so now we're going to look at secant. For secant, x and y are the x values will all be the same. So we're going to have 0, pi over 4, pi over 2, 3 pi over 4, and pi. And now the y values are going to be the reciprocals. The reciprocal of 1 is 1. The reciprocal of 0 is undefined. So what does that tell us? That tells us that there's a vertical asymptote at x equals pi over 4. Then pi over 2, the reciprocal of -1 is -1. We have another 0, so we have another undefined. Therefore, we have another vertical asymptote. And then the reciprocal of pi is 1. The reciprocal of 1 is 1 at pi. Okay, so what is this going to look like? Pi over 4, we have a vertical asymptote. And where else do we have one? 3 pi over 4. So it kind of looks like we're going to have vertical asymptotes just to fill in the rest every other one. So then there'll be one right here. And you can see where do these vertical asymptotes occur? They occur where cosine was at 0. So anytime cosine's at 0, we're going to have a vertical asymptote. And then there's going to be a vertical asymptote here. Now this graph is going to look a little strange, so rather than starting at 0, 1, because that's going to be like half of a graph in between the asymptotes, I'm just going to slide over my cosine secant graph and work with in between the first two asymptotes that I drew at pi over 4 and 3 pi over 4. What other information do I know? Well, I know that there's going to be a matching point here, and I know that this graph is not going to be in between -1 and 1. So that indicates to me that we're just going to have this downward, almost like a parabola in between the asymptotes there. So it looks like the rest of the graph will be in between 3 pi over 4 and 5 pi over 2. And we know that at pi, we have a point here on secant at 1. And the rest is going to be going up, coming down, and then back up. So there's one full period. Now let's do another full period. So we're going to go over here to -1. We're going to see it repeat. And then, looks like I have, so I would have like pieces of graphs. I could have, one here, and then I would have one here. But just for consistency's sake, we'll just finish the graph on one side just so it's totally complete. Our periods are going to be a little bit different, but that's okay. And we would have one there. So you can see the blue is our cosine graph, and the red is our secant graph. And these both represent cosine of 2x and secant of 2x. Okay, in this example, we have sine of x over 3 and cosecant of x over 3. For sine, let's look at the information that we know. It looks like our amplitude is 1, and our b value is 1/3, so we're going to use that to determine the period. The period is found by taking 2 pi and dividing it by 1/3. 2 pi divided by 1/3, that's equivalent to multiplying by 3. So our period in this case is 6 pi. The increments that we'll use to set up our table, we'll take the period and we'll divide it by 4. 6 pi divided by 4 is 3 pi over 2. So the increments we want to count by are 3 pi over 2's. Let's create a table of values for our sine function. 2, 3, 4. We're going to start at 0 since there was no horizontal shift. And we're going to go up to, or count by 3 pi over 2. So 0 plus 3 pi over 2 is 3 pi over 2. 3 pi over 2 plus 3 pi over 2 is 3 pi. 3 pi plus 3 pi over 2 is 9 pi over 2. And 9 pi over 2 plus 3 pi over 2 is 6 pi, because it would be 12 pi over 2. And that matches our period, so I feel pretty good about that. All right, what are the corresponding y values? This is a sine. Sine starts at the midline, goes up to the top, back to the midline, down to the bottom, back to the midline. Since the amplitude is 1, we're going to start at 0, 0, go up to 1, back to 0, down to -1, back to 0. Let's sketch a graph of this sine, and then we'll look at the cosecant next. So sine, we have 0, 0. We're going to count by 3 pi over 2, so that's 3 pi over 2. This is going to be 3 pi. This will be 6 pi. This will be 9 pi. And this will be 12 pi. And we have 3 pi over 2, 1. So 3 pi over 2 is going to be right here. Then we're going to go down to 3 pi, back to 0. At 9 pi over 2, we're going down to -1. At 6 pi, we're going back to 0. So there's one full period, but let's do that again. 6 pi starts us, so next we would have 12 pi, 15 pi over 2 would go up to 1. 9 pi would go back to 0. 15 plus 6, 21 pi over 2 would go down to -1. And then back to 12 pi. Nice smooth curve for our sine. And there's 2 periods of our sine graph. Let's look at our cosecant graph. I'll set up my table for cosecant. And the x values will be the same. So we're going to have 0, 3 pi over 2, 3 pi, 9 pi over 2, and 6 pi. And then we're going to look at the reciprocals of the y values. Okay, starting at 0. It should be 0, but that means that we're going to have an undefined. That means we have a vertical asymptote at x equals 0. The reciprocal of 1 is 1. The reciprocal of 0, we have another undefined. We have another vertical asymptote here. So we have a vertical asymptote at x equals pi over 3. The reciprocal of -1 is -1. The reciprocal of 0 is undefined. We have another vertical asymptote at 6 pi. So what does this look like? I'm going to draw in the asymptotes. And again, the asymptotes should line up right where the x-intercepts are on our sine, because we're taking the reciprocal of 0, which is impossible. So it looks good. Just going to keep going. and 12 pi. Okay, this one will be a little bit neater than our cosine graph, so that's nice. All right, so what do we have? We have that, then we have 3 pi over 2, 1. So those should match up, so that's good. And that indicates that we're going to be above here, so it's going down. And it's almost like, you know, it's like very parabolic looking. Then down here at -1, we have like a negative, looks like a negative quadratic. Back over here, it repeats. So we just completed one full period here between 0 and 6 pi. Now we're going to look at between 6 pi and 12 pi. We go up, and then we meet here again at -1. And we have one that faces down. And this would be 2 full periods of sine of x over 3 and y equals cosecant of x over 3. Okay, in our next example, I encourage you pause the video and try it out and see how you do. Let's see what this one looks like. We have cosine 3x minus 1. The 3x would be inside parentheses. That -1 indicates that we do have a vertical shift. Okay, so we know a is 1, so the amplitude is 1. B is 3, so how does that help us? That helps us determine the period. The period is 2 pi over 3. C is 0, but D is -1. So what that indicates to us is that our midline for this graph is at y equals -1. So we're dealing with a downward shift of 1 unit for this graph. Okay, so next, the increments that we're going to be using for this to help us out. We take the period, 2 pi over 3, and we divide it by 4. Dividing by 4 is the same as multiplying by 1/4, so I'm going to go ahead and do that. And we're going to end up with pi over 6. We're going to be counting by pi over 6s as we go. Set up my table. We have x and y. Find our 5 key points here. We are starting at 0, and then we're going to count by pi over 6s, so pi over 6. This would be 2 pi over 6, which would be pi over 3. This would be 3 pi over 6, would be pi over 2. And then this would be 4 pi over 6, which is 2 pi over 3. It should match our period, which it does. Hooray. All right, now, this is tricky because we do have that shift down. So we know that with the cosine graph, it should start at the top and then go down to the middle and then to the bottom and then back up to the top. But we're shifting down 1 unit. So I'm actually going to start at the second point because this is where the midline would be. I'm going to start at pi over 6, and pi over 6 is going to be at -1. It's going to be where that midline is. Also, pi over 2 will be at -1. Since the amplitude is 1, kind of working backwards here, 0 should be 1 unit above -1, so it's actually going to be at 0, 0. Oh, that's very sign of it. And then here, we're going 1 unit below -1, which would be -2. We go back up to the top at 0. So our cosine graph is going to look like 0, 0. This we'll call pi over 6, but I'm not going to label it just for my own sanity and keeping this neat. We have pi over 3 and 2 pi over 3. So pi over 6, we're down at -1, down at that midline. Then we go down to -2, back to the midline, back to the top. And then we can repeat this. So we'll go back to the middle, to the bottom, to the middle, back to the top for 2 full periods. So this is what our cosine graph will look like. Now let's look at our secant graph. Setting up our table, we have x and y, and we have 0, pi over 6, pi over 3, pi over 2, 2 pi over 3. Now the tricky thing here is with that vertical shift, basically anything that's on the midline for cosine is an asymptote for secant. So that means we have asymptotes here at pi over 6. This is going to be undefined, even though it looks like, wait, no, it's the reciprocal, but it's a little bit sneaky because of that shift down. So it's going to be undefined. We'll have a vertical asymptote there. We'll have a vertical asymptote here at pi over 2. So the asymptotes occur where the graph hits the midline, courtesy of that vertical shift. It's kind of moving everything down 1 unit. And here. Okay. So then, what do we have? Well, we'll have 0, and this is going to be really weird because remember, everything's moving down 1 unit. So actually, this secant graph is going to have a point at 0, 0. The points that are not asymptotes on these key points are going to match. So we have 0, 0, we're going to have pi over 3, -2. and then we'll have 2 pi over 3, 0. And if you're a little bit weirded out by it, you can always plug in the point. So if you plug in 0 here, let's go to the actual function. This would be secant of 0 minus 1. And secant of 0 is 1, 1 minus 1 is 0. So it checks out that if we actually plug in 0, we get 0. So a little bit tricky when we do have a value for d, and if you feel more comfortable, you can always plug into the function. But we do want to use that cosine graph to help us. So now we're going to have a point here, a point here, a point here, a point here. And I'm just going to complete one more asymptote just so we have, that's probably the wrong one to do. Let me go over here. Just so that way the period starts with a negative and ends with a positive, which is what it should do. And then I'm going to start with this one. It's going to look like a downward facing parabola, followed by an upward facing parabola, followed by that was one full period. So from here to here was one period. Then here, and it would be here. So that's what our secant graph would look like. So cosine is in blue, secant is in red. In our final example, we want to sketch a graph of y equals sine of 2x plus pi over 6 and y equals cosecant of 2x plus pi over 6. Let's start with our sine graph. So we have sine of 2x plus pi over 6, and we can identify a is 1, b is 2, c is negative pi over 6, right, because it's the opposite of what we see, and d is 0. This helps us identify the amplitude, which is the absolute value of a, is 1. We can figure out the period, which is 2 pi divided by b, 2 pi divided by 2 pi divided by 2 is pi. And we have a phase shift this time. So the phase shift, since we do have a horizontal transformation here, we determine that by doing c over b. So this would be negative pi over 6 over 2, and that would end up being negative pi over 12. So everything's shifting negative pi over 12 units. Now we might want to make our table of values for our sine graph. So we have x and y. And let's remember where we're starting. So rather than starting at 0, we're shifting over to negative pi over 12. Whoops, one thing I forgot to do was figure out the increments. The increments that we want to use come directly from the period. The increments, that's when we take the period and we divide it by 4. So we want to count by pi over 4s. We will have to do some adding of fractions, and I think since we're going to have denominators of 12, we might want to consider our increments to be 3 pi over 12, right? Because that's multiplying by 3 over 3. So that might make our lives easier to just have that there, and we'll use that. So to figure out the next x, we're going to take negative pi over 12 and add 3 pi over 12 to it. That will be 2 pi over 12, or pi over 6. But if we think about it as 2 pi over 12, now we can add on the next value, or figure out the next x value. 2 pi over 12 plus 3 pi over 12 is 5 pi over 12. Now we're going to add another increment to that. 5 pi over 12 plus 3 pi over 12 is 8 pi over 12, and that simplifies down to 2 pi over 3. And then 8 pi over 12 plus 3 pi over 12 is 11 pi over 12. Whew, okay, so we figured out our x values. How about our y values? Well, the good news is that there's no vertical change. So sine should start at 0, 0. This time it's going to start at negative pi over 12, comma 0. The amplitude is 1, so we get to just use the amplitude to guide us. We're going to go up to 1, back down to 0, down to negative 1, back up to 0. And that's going to tell us one complete period. On my graph, I'll count by units of pi over 12s, since that's what it looks like we have here. So here's negative pi over 12, 0 pi over 12. 1 pi over 12, this is 2 pi over 12. 3 pi over 12, 4 pi over 12, 5 pi over 12. 6 pi over 12, 7 pi over 12, 8 pi over 12. 9 pi over 12, 12 pi over 12, what did I do here? 8 pi, 9, 10, 11. I know how to count, I do. 11 pi over 12. And here's negative pi over 12. Okay, so we can go ahead and sketch a graph of this. So we have negative pi over 12, 0. Then the next one, pi over 6, we're going up to 1. At 5 pi over 12, we're going back to 0. At 2 pi over 3, we're going down to negative 1. And then we're going back to 0. Now, to get a second full period in here, I think I'm going to have to go to the left. So since it looks like the increments are counting by 3s, 1, 2, 3 will be a point. 1, 2, 3 will be a point. 1, 2, 3 will be a point. One more. Oh, I just barely make it. So right over here, this starts a period, so it's going to go 0. At this one, it's going to go up to 1, back down to 0, down to -1, and we do get back to 0, so that's good. So this is going to look like wee, wee. Gorgeous. There's our sine curve with 2 full periods. Let's check out cosecant. Our table for cosecant, remember the x values are going to be the same. It's the y values that we're interested in the reciprocals. And we don't have any tricks like we did with our previous example with the secant and cosine because we don't have any vertical shifts, so that's good. So zeros really are asymptotes. Just trying to get this set up, and 11 pi over 3. Okay, so this is going to, that's going to be undefined. There's a vertical asymptote. This will be 1, undefined, -1, undefined. All right, and again, anywhere we see an x-intercept, or really what it is, it's anywhere that's on the midline, that's going to be an asymptote of the reciprocal function. So we're going to see one here, and here at -π/12, here at 5π/12, and then lastly at 11π/12. Then the points should match the secant points. The minimums should match the maximums of the sine, and the minimums of the sine should match the maximums of the cosecant. So we have a point here. It's going to kind of look like a parabola shape wedged in between those asymptotes. We have a point here. It's going to look like a parabola shaped wedged in between asymptotes. And again. And one more time. So we see we've sketched 2 full periods of sine and cosecant of 2x plus π/6. Cosecant is in red, sine is in blue. This has been a video on looking at cosecant graphs and secant graphs. Thank you for stopping by.